Okay, can I see? Okay, welcome to this last part of this last lecture, in which we will see some phenomenological application of the formalism that we have developed in the first part, and I will just give you some feeling of the setup that you must put together to perform a realistic study. So in Torino we developed this setup that we called the POLANG, because we have essentially interfaced the output of the POEG box event generator with some Langevin transport calculation. So the approach is more or less the following. You must simulate the initial QQ production, and this you do with the POEG box package, but you can use any other PQCT automated tool. You supplement this code with the information on the nuclear PDF, so you will use modify the parton distribution functions, which in a nucleus are different than the ones in a proton. Then you will distribute the quarks that you produce in the transverse plane according to the local density of binary collisions. Since this is a RPQCT process and you expect that it scale with the local density of binary nucleon collision, okay? And this is information you get from a Glauber model, either in a optical or Monte Carlo implementation. Then you must perform the update, the momentum and positional update of the quark with the Langevin equation, but this update can be performed step by step in the local fluid rest frame. Hence you need two information. First of all, the information on the collective motion of the fluid, okay? In order to boost back and forth from lab to fluid rest frame and go back to the lab frame, in which at the end you measure the observables. And then you must know the local value of the temperature, since this local value of the temperature will be reflected in the value of the transport coefficients which enters in the Langevin simulation, okay? And this clearly it's an information that you must take from the output of some hydrodynamic calculation validated in order to provide a realistic description of the soft particles that you produced in the same collisions, okay? And then you must iterate the procedure until hadronization, and possibly also take into account of modification of hadronization in the presence of a medium, okay? So this was a study, for instance. Here I show you the study of this carried out by this group, in which I think it's very interesting, because they tried to check that also in the case of an expanding medium, they are able to correctly describe physics. And so which was their strategy? Their strategy was to perform a transport simulation with very, very large transport coefficient, so that it should be guaranteed that you approach local thermal equilibrium with the medium. And if this is the case, the point is that your heavy quarks will decouple as exactly the other hadrons from the fluid. So you can study the heavy quark single particle distribution as you do for other hadrons. So just in terms of decoupling from some freeze-out hypersurface, okay? And this is what they did. They compare essentially the green point, which are the point coming from the Langevin simulation, with the red curve, which is a freeze-out curve. So this would be what one would obtain in the hydrodynamic limit, in which we have full kinetic equilibrium. And you see that up to quite large PT, the curves perfectly overlap. Okay, and both for the momentum, the PT spectrum, and for the elliptic flow. Okay, this, these observables this observable that we studied in the previous lectures. So another check that you can do is how reliable, how restrictive is this condition on the charm mass with respect to the typical momentum exchange with the medium. So because although it is a convenient numerical tool, because it links observables with the transport coefficient. Observable is something that you measure with transport coefficient. It's something that you can calculate in principle. I mean, the Fokker-Planck or Langevin equation is in any case based on a soft scattering expansion of the collision integral. So how justified is this expansion can be a matter of debate. So what they did, for instance, is to compare the ratio of the spectra in the Langevin with respect to the Boltzmann equation, and you see that clearly, depending on the temperature of the medium, if the temperature is large enough so that momentum exchanges are not so small compared to the charm mass, you can have deviation with respect to the Boltzmann equation. And on the other end, for the bottom, you see that the two approaches are perfectly equivalent. Okay, so this was quite an interesting study. Then the point is to have some tool to evaluate transport coefficients. In the literature, people follow the several strategies, either perform a weak coupling calculation in HotQCD, either trying to extract the information from lattice simulations, either they use this ADS CFT correspondence, or did some other assumptions, like that momentum exchange in the medium comes from some resonant scattering mediated by some meson-like resonance present in the medium. Okay, so I will just sketch the result of two of these approaches. So the first kind of approach is to evaluate this transport coefficient as coming from 2-to-2 collisions, in which one can provide a separate treatment for hard collisions, which are the one in which I exchange a large momentum, and soft collisions, which are the ones in which I exchange a soft momentum, by introducing some intermediate cutoff of order of the Debye mass. And so hard collisions comes from these PQCD processes. Okay, you evaluate the interaction rate of your heavy quark due to these scatterings, and just you weight this interaction rate with the squared momentum exchange in these processes. Soft collisions are collisions which are mediated by long wavelength gluons. So if these gluons have a long wavelength, they feel the presence of the medium. So I must insert in the propagator some medium modifications, which are given by this thermal self-energy, which can be evaluated, for instance, in some approximation like the so-called hard thermal loop approximation, which is an approximation that probably we discussed in the lecture on plasma physics. Okay. At the end, these are the results. On the left for charm, on the right for bottom, as a function of the quark momentum. Okay, I plotted the results up to very large momenta, even for momenta which are no longer, for which it is no longer so well justified to employ this picture in terms of uncorrelated 2-to-2 collisions. And you see that these are the results for the transport, and these are the results for the longitudinal momentum diffusion coefficients. These two curves are very close, and depends on this changing this intermediate cutoff separating hard and soft collisions. So you see that the results is not so sensitive to this arbitrary cutoff, and this is the same for beauty. And so you see that as you go to large momenta, the momentum dependence of the transport coefficient is there. It's quite important, and in particular the two longitudinal and transverse differs quite a lot. Clearly, due to the very large mass for bottom, this effect is milder. Okay. This is the same. This is what you get deriving from this transport coefficient, the friction one, applying the Einstein relation. Okay. Now, the other possibility is to evaluate, try to evaluate transport coefficient from lattice QCD simulation. Clearly, we must mention that there are some difficulties, and the major difficulty is due to the fact that transport coefficients are real-time quantities, while lattice simulations are performed in a Euclidean space-time. So time is imaginary, and it means that I have sacrificed the possibility of studying the time evolution. So I mean, in principle, lattice QCD calculations provide a non-perturbative answer, but there is this major difficulty in extracting real-time quantities from Euclidean simulations. Okay. So far, I would say that the most reliable result for the heavy quark transport coefficients are obtained in the following setup. So one consider essentially the case of having a static heavy quark placed in a plasma. Okay, a static means infinitely heavy, so it doesn't move. It is just a color source placed in a certain position. Okay. So in this case, the Langevin equation can be written. It's not in its non-relativistic form, in which here I can neglect the difference between transverse and longitudinal, and also the momentum dependence of this kappa. Okay. So remember, in general, I have a kappa transverse and a kappa longitudinal. Here I have just a kappa, and if you take, you see that from this time correlation, you see that if you integrate this time correlation from minus infinity to plus infinity, due to this delta function, you get simply kappa, okay, times 1/3 from the sum of the indexes which are contracted, okay. But in the P to 0 limit, this is nothing but a force-force correlation, okay, because clearly this is a force. In the P to 0 limit, the friction term is not important, and so this is nothing but a force-force correlation function called d bigger, because the force as time t at time t appears on the left of the force at time 0. So usually these correlators in thermal field theory are called d bigger. Okay. In the limit in which the quark is infinitely heavy, the only force which is relevant is the color electric field, okay, because magnetic forces are not important. So this is nothing but the quantity that I want to evaluate in order to extract kappa is an electric field correlator, okay. And you can show that, notice that this is nothing but the zero frequency limit of its Fourier transform. Okay. Now, if you, I don't know if you attended some classes in thermal field theory, but in any case, due to the essentially due to the periodic boundary conditions along the imaginary time axis for bosonic fields, you have a relation between the bigger and the lower. The lower will be the one in which F0 appears on the left. This relation is called the Kubo-Martin-Schwinger relation. So that the bigger, if you wish, you can express in terms of this spectral density of this correlator. Okay, now you can expand in, remember you are interested in the zero frequency limit, because here you have this integral from minus infinity to plus infinity. So you can expand this for small frequencies, and you get this result. So essentially, kappa comes from the zero frequency limit of sigma omega over omega. Okay, so it means that you must know sigma omega really very, very well, close to omega to 0. Now the point is that I mean this object can be evaluated just at imaginary times. These are Wilson lines, which are there because I'm evaluating this expectation value in the presence of a static heavy quark, which evolve in time according to some Wilson line. Okay. So this is this electric field correlator which I must evaluate. This can be evaluated on the lattice, and the relation between this and the spectral density is given by this integration over in which there is this convolution over this thermal kernel. I don't know if you have seen already this, but essentially it is this comes from the fact that this don't know if I have called the D. How do I this D O tau, since T is equal to minus I tau, is nothing but D of the bigger evaluated at T equal minus I tau. Now this the bigger you integrate, it comes from the integral d omega over 2 omega from minus infinity to plus infinity e to the minus e omega t, but where now t is equal to minus I tau times the bigger of omega. Now the bigger of omega you express in terms of this spectral function, and then you split this integration from 0 to infinity and to minus infinity to 0. You do some change of variables, and then exploiting this relation, you are left with this kernel. Okay, you can check that this is what you get. So, but besides these details of the derivation, which is the message, is that you need to extract this. So you want to extract its functional shape, and you want to know it very accurately, close to omega to 0. Okay. But the point is that you can imagine to have some bin, and the value of this function in each bin is like a fit parameter, let us say. But the point is that so you have thousands of these free parameter to fix on top of these quantities, which is known for just from a limited set of point and with some statistical error. So the point is that this is a ill-defined, ill-posed problem from the mathematical point of view, and so you must develop some proper inversion technique of this transform, which are based on a method like maximum entropy method or other Bayesian techniques. Or okay, of course, another strategy is to take to assume to give an ansatz for the functional form of this sigma, and to an ansatz depending on a few parameters, and fit these few parameters on top of this data. But of course, now here you introduce a systematic error in the fact, due to the fact that okay, depending on the functional form that you take, you get different results. Okay, in any case, these are more or less the results that you get for k kappa over t cube. You get a number around 2.6, but with a quite large systematic error bar, with a quite large systematic band. You see this. I think that all these are all different somehow ansatz for these functions, which provides a quite large systematic error band, okay, for the result. And furthermore, you don't have any more information on the momentum dependence, because this calculation has been performed just in the limit of a static heavy quark at rest, so at zero momentum. Okay, in any case, it's better than nothing. Okay, these are details which I can skip. So, in light of what we have seen, one can say that for beauty in particular, beauty measurement are particularly interesting for because we have seen that in this limit for very large mass, the Langevin and the Boltzmann equation provides identical result, and the fact that the mass is very large also makes the lattice QCD estimate of the transport coefficient more reliable. Okay, so here what I have done is a comparison between the experimental data obtained by the CMS collaboration for the displaced J psi. So these are J psi which comes from the decay of a B meson. Okay, these are J psi which comes from the decay of a B meson, and here this is the RAA as a function either of the centrality of the collision. These are the average number of participant nucleon in a nucleon collision, nucleus-nucleus collision. So these are central events, and these are peripheral events, and these are results from as a function of PT, and compared to different theoretical calculations. Okay, now these results were obtained with vacuum fragmentation functions. Then in the following I will show you the results obtained by performing some in medium hadronization. So heavy quarks are produced here, they propagate in the medium. At a certain point they reach a freeze-out hypersurface where they can recombine with some thermal parton extracted from the medium, and this thermal parton will transfers to the final hadron also some of its collective motion. Okay, so let us check what do we get. So these are results for D mesons. This is the nuclear modification factor. This is the elliptic flow. These are the meson measured at star, and these are the meson measured at Eris. So these are RIC and these are LHC results. You see, star results, which goes to very low PT, are characterized by this bump at moderate PT that you would like to interpret. And Eris results are characterized by this non-vanishing elliptic flow of the D mesons. So you would like to understand whether this can be a signature of the fact that the charm, as in propagating in the medium, has reached full thermal equilibrium with the medium, so that it has acquired the collective flow of the medium. So it has this collective radial flow and also this asymmetric flow in the azimuthal plane, because in practice it is like this. The interpretation would be that charm flows together with the medium, which has this collective behavior. So the curves are curves obtained by with hydrodynamic calculation. So it means that once we have simply performed hydrodynamic simulation of the medium, and then we applied this freeze-out decoupling technique just for a D meson. So assuming that a D mesons, so we have not studied the transport of D meson, but we have simply assumed that the D meson has reached equilibrium, and what would be its spectrum in this case. And you see that you reproduce more or less the this bump in the spectrum. So clearly, if the charm is fully thermalized, its spectrum at IPT would be exponentially suppressed. Okay, so you see that this is not the case. But however, you can imagine that for more moderate PT, charm is thermalized, and so this would explain this bump in the RAA. So the interpretation would be I have a part of charm which initially had a smaller transverse momentum, but then it is pushed by the collective motion of the medium, and I have some particles which acquire some collective transverse momentum. Okay, so this could be a possible interpretation. However, and the same for the collective flow. However, the situation is not so clear in the sense that here the data are the same. Here I have shown you in green, you see the result of the hydrodynamic limit. Dashed lines are the lines of transport calculation, so are really simulation with the Langevin equation. But then, in which then at the end, once the heavy quarks decouple, they are hadronized like in the vacuum, so with independent fragmentation functions. And you see, you are not able to reproduce this bump. However, by deciding to model hadronization in a different way and recombining charm with light thermal partons, you see that you get again a structure displaying a bump. And notably, I mean, first of all, you reproduce better the fact that at large PT you don't have a completely exponential suppression of the spectra, but the region in which this bump occurs is more or less the same as in the case of the full equilibrium, so the point is the following. The data are not able to tell you whether the fact that there is this bump comes from the fact that the charm has reached the full kinetic equilibrium, or whether charm has not reached the complete equilibrium with the medium, but since it hadronized combining with some particles that are on the contrary, which fill this collective flow, there is this additional collective flow acquired at hadronization, which can moves the data in quite close, the theory curves in closer to the experimental data. So you see, this is the same for the elliptic flow. You see, the elliptic flow acquired in the partonic stage is not so large. So these are hadrons, charmed hadrons, coming from the hadronization of charm, but just with independent fragmentation functions. Here are the same, but in which the same charm quarks, after the propagation in the medium, are hadronized by recombination with the medium particle, and again you see that the additional elliptic flow inherited from the medium particles move the curves closer to the data. Okay, so and more or less this is this is the effect that you can get also at other collision energies and from the comparison with the different experiments. So I skip this part. These are data, more recent data, analyzed again by the STAR experiment. This is the elliptic flow measured in gold-gold collisions at 200 GeV at RIC. These are the experimental data, and these are the theory curves, including this medium hadronization. And these are CMS, more recent CMS data in lead-lead collisions, again the elliptic flow, in peripheral collisions at 5.02 TeV. So these are the most recent experimental data. Again, these are the experimental results. These are the theory curves with different choices of the transport coefficients, and with again this medium hadronization. Okay. Okay. Finally, I just sketch you some result on heavy flavor in small systems. So why this is interesting? Because we have, you may have seen, you have seen in the hydro lectures that there are signatures of collective effects also in the collisions of small systems like high multiplicity proton nucleus collisions or deuteron nucleus collisions, or even high multiplicity proton-proton collisions. Okay, you have seen that focusing on soft hadrons, you have seen this elliptic flow, this triangular flow, this long-range rapidity correlations. Okay. Now the question is: are there signatures also for what concerns heavy flavors? So, because the point is that we have also seen that for what concerns, on the other end, the jet quenching, we have seen that, for instance, as a function of Pt, this R P LED turns out to be compatible with 1, so that we can say, well, concerning hard probes, we don't have a signature of any medium effects. So how to reconcile these two pictures? That the fact that the RP LED is compatible with 1 within experimental uncertainties, and the fact that on the other end, concerning soft observables, one observe non-trivial medium effects. Okay, so I observe a V2, a V3 different from 0, but I don't observe any signature in the RAA at IPT. How do we reconcile this? Well, remember that the average energy loss, let us use this pocket formula, has this dependence on the coupling, on Q hat, this transport coefficient, and on the length of the medium. Now, just from dimensional reasons, this Q hat should have a dependence on T cube, okay? And the length of the medium, there is this L square dependence for what concerns the length of the medium. So I have a strong dependence on the medium thickness and on the temperature of the system, okay? On the other hand, let us check what happens for what concerns soft observables. So, if we assume the soft observables are described by hydrodynamics, it means that I have this is a strong assumption, but let us take it as a working assumption. It means that the expansion of the medium is driven by pressure gradients. Okay? Let us take as an initial condition this Gaussian distribution for the entropy density. Okay? And employ the Euler equation to describe the acceleration of a fluid cell driven by pressure gradient. By employing the equation of state, you see that the fluid acceleration is given by this formula, and if you solve, you get that essentially the average radial velocity depends on the speed of sound square, but the speed of sound, I mean, is quite constant. It can vary by a factor by 50%, but it always stay not too far from 1/3. Okay, and on the other hand, if the system is small, I mean, this radial flow is even larger. Okay, of course the lifetime is shorter, but it can be compensated by the fact that the initial size of the system is smaller, so the gradients are larger. Okay, and so it's not completely incompatible, the fact that you don't observe a strong jet quenching if the system is small, and the fact that you observe on the other end a strong collective motion. Okay, so the question could be, what happens to heavy flavor? Okay, the experimental situation is more or less the following. For instance, this is the nuclear modification factor of the mesons at Elis, at LHC, and you see, of course, experimental data are still quite large systematic error bars. these are non-photonic electrons, so these are electrons from heavy flavor decay. So these are electrons from the decays of charm and the beauty hadrons, measured at Rick in deuteron gold collisions. And you see that in more central event, you have this they stay systematically above 1, okay? So the question could be, well, and this occurs for more central collision, not for more peripheral collision. So the question could be, is this a signature of some medium effect? So what one can do is to try to employ this same setup. Also in this kind of collisions. Of course, in this case, I mean, the difference is the following. While in nucleus-nucleus collision, I can provide a picture based on the Glauber model and say, okay, if this is a cartoon of the transverse plane, I can have some matter in this overlap region, and I can provide a geometric description based on the Glauber model. Clearly, if my projectile is a nucleus, is a proton, I mean, this geometric interpretation fails, okay? So, I mean, in order to model the initial spatial asymmetry of the system, I must really perform a event by event study in which the spatial asymmetry comes from the random position of the nucleons in the target nucleus, okay? So that a spatial asymmetry these clearly are the nucleons which interact with my projectile, and the spatial asymmetry comes from the event by event fluctuations of these target nucleons. Okay, so you must rely on some Monte Carlo modeling of the initial condition, and you can imagine, for instance, that each binary nucleon-nucleon collision is a source of entropy density in the transverse plane. And then, of course, at the end, we, in order to avoid having to evolve thousands of initial conditions, we took some average initial condition obtained by averaging all these events. And this is a cartoon of the initial condition, and this is the resulting elliptic flow for different initialization that you get for the light hadrons. So these are pions that you would produce, and these are experimental results from ARIS and CMS. So this was just a validation of the background of the modeling of the background. Then if you perform the Langevin evolution within this background, you see these are the results that you get. Blue and orange curves are theory curves with different transport coefficients. The band comes from the some freedom in the initialization, and you see that okay, clearly at LHC the experimental error bars are so large that you are not in a position to say whether there is or there isn't or there is not a medium effect. But I mean, if you rely on these results at RIC, it seems that I mean, at least they are not incompatible with the possibility that you produce a medium in these collisions in which you produce a medium which is able also to mildly, but in a negligible way, affect the result also for HeavyFlavor. Okay, so this is more or less the end of the story. And okay, nowadays clearly there are attempts to do better, for instance also to extend the analysis to observables to more forward rapidity by performing full 3+1 simulation for the hydrodynamic background. And okay, and clearly this issue of static collectivity in small system really it's an issue of it's a hot issue of investigation in the community in this period. Okay, but I think more or less I have sketched both the development of the formalism and I give you some feeling of the results that one can obtain by applying this formalism to face a realistic situation. There are questions? Okay, if not, we can stop here. Thanks also to our team.